So yes, so I wanted to talk a bit about reionization and 21 centimeter cosmology. So in particular, I will focus on reionization for quite some time. So the idea is I want to cover a bit of the physics behind reionization without worrying about what you can use reionization for. I mean, without worrying about dark matter and other things for the time being. So just conventional standard reionization. And then I will talk about observational probes of reionization, which we already have, and then also 21 centimeter experiments, which are like kind of coming up. And towards the end, I will talk a bit about how to probe dark matter using reionization observations. Here you will find a lot of overlap with what I talked about in the morning, but still, just to complete the story and keep this talk self-contained, I will do that. Now, the references which we have is, I mean, most of the things, I mean, there are many things which are in the textbook and which I won't cover. And a nice textbook which like kind of covers many of these things, including cosmology, is this Galaxy Formation and Evolution by Moe, Van den Bosch, and White. This is relatively recent. I mean, recent meanings it's still probably almost a decade old by now. And then a review article I wrote a couple of months back. It's called Short Introduction to Reionization Physics, and this is the archive ID, so you can take a look at this. So many of the things which I'm going to talk about, the details you can find in the review article. So let me come back to the picture we had in the morning. So reionization is basically you have this first hydrogen atoms forming at the last scattering epoch, followed by a phase of dark ages, no galaxies, nothing. All matter is kind of neutral. Cosmic dawn, the first stars forming, and hence starting to ionize the neutral hydrogen in the intergalactic space. And this is reionization, where all these ionized regions come together and eventually ionize the whole universe. And after that, you have this post-reionization era. And as I will try to convince you that this picture is kind of confirmed by many different experiments, except the details are not very well known. So suppose I want to kind of model or understand all this physics which I talked about. So what are the things I need? What are the ingredients to this modeling or understanding this reionization? So the first thing we need are the dark matter halos, because that is where eventually stars and galaxies will form. And dark matter halos are basically the part of the dark matter, very dense, and they have kind of decoupled from the underlying expansion. So initially everything was expanding with the universe, but regions which were slightly overdense grew more and more overdense. Then because they grew overdense, then they slowly basically decoupled from the expansion, that what we call turned over, and then started collapsing, okay, and then formed what we call a virial structure. Now, the gas basically just follows dark matter, because dark matter is the dominant component. So the gas, I mean, gravity-wise, the gas is not going to do much except just follow wherever there is more dark matter. Dark matter will attract all the gas towards them. So basically, the gas basically falls into this dark matter halos. You think of these dark matter halos as potential wells, hence it falls. And then all sorts of physical processes have to take place, like cooling, fragmentation, feedback. So basically, all these galaxy formation physics will have to happen. So this is something also in principle we should try to understand if we want to study reionization. Once you form stars, you need to know their spectra. So stars have formed. So you know that, okay, I have 100 stars of this solar mass and 200 stars of that solar mass and 150 stars of this solar mass. Fine. But how many photons, I mean, what kind of radiation are they producing? In particular, we will be interested on the number of ionizing photons they are producing. That will tell us how many hydrogen atoms they will eventually ionize. So these are basically done by what are known as population synthesis models. So these basically track how stars form their main sequence and throughout their age, what kind of radiation they are producing. And some of these population synthesis models are publicly available, so one can just go and study them or implement them in your reionization codes. After that comes something which is so uncertain. I mean, it is very difficult to model. It's very difficult to constrain observationally. That is, you have produced these photons, but there is a lot of neutral hydrogen in the galaxy itself. So many of the ionizing photons will be consumed then and there. Okay. So imagine the extreme case where there are so many neutral hydrogen atoms that all these ionizing photons are consumed inside the galaxy and nothing comes out. Then there is no reionization of the universe. You have produced stars, you have produced ionizing photons, but they haven't come out to the intergalactic space. So, which means there has to be this escape of photons from the galaxy, and in case they cannot escape, we have to then go and look for much more exotic sources of reionization. Remember, as I said, this is not very well understood as we speak now, because it is not just you count the number of neutral hydrogen atoms and number of ionizing photons present. It doesn't work that way, because in the galaxy, the neutral hydrogen is extremely clumpy. Okay, what we call interstellar medium. So depending on how clumpy they are, how many kind of regions like channels it can form where the photons can escape. What can sometimes happen is there could be like violent events in the galaxy. They can kind of remove some of the gas and create passages for photons to escape. All sorts of complicated things can happen. So this is something which we really don't understand. People do simulations, people try to understand that, but I mean, we don't have a consensus there as well. Then once assuming that this escape has happened, some fraction of photons have escaped, what will then you need to know is, I mean, how this ionization fronts, I mean, how these ionized regions are basically propagating through the intergalactic medium. For that, you have to do radiative transfer. So you have to basically do all these things to understand reionization in principle. The whole thing roughly, I mean, it's various things are coupled, but roughly you can divide this whole algorithm into 3 blocks. The first block relates to cosmology and structure formation, where basically those tell you about the dark matter halos in the universe. The second part talks about, deals with galaxy formation and interstellar medium. So you're talking about things happening inside the galaxy. And the third part is radiation in the intergalactic medium, basically, how this radiative transfer is happening. Okay. So roughly these 3 blocks have to be dealt with in some way or the other. One should not forget that you can make a reionization model, but eventually you have to compare with observations. So you have to find a way to calculate the observables, whatever the observations predict in some way. And eventually, hopefully, you should be able to do statistics with those observables and hence try to constrain the parameters of reionization or whatever you are interested in. So this is roughly what people are after, at least theoretically. Fine. So let us delve into some details of each of these. Now, dark matter halos are basically very well, this is one part which is probably the best understood in the whole problem, because dark matter halos, you are dealing basically only with gravity, assuming that dark matter is this conventional CDM. You have to just worry about gravity, and that is very well done by numerical simulations. So basically, you will run a numerical simulation, and then you will find places where particles have come together and formed groups, and then you will identify those groups using some group finding algorithm, and then you will get something like this mass function. This is something which I showed in the morning as well. And this mass function has a typical feature. It is kind of power law at low mass end, then it kind of drops down exponentially at large mass ends. And yeah, these are for different redshifts. So you can see as you increase redshift, at higher redshift, the number of halos are less, basically kind of less structure formation. And top of that, number of high mass halos is really less. Okay, so that is how things go. What you can also do, I mean, as I said, this is something which we understand reasonably well, is that some of these mass functions can also be understood analytically, and that is what is something good about like gravity only systems. So what you basically need, I won't go into the details, what you need to know is linear perturbation theory, which I believe you have learned in the first week. So basically how the density contrast of matter distribution evolve in the linear theory. This is something which can be like worked out analytically without any difficulty. This you need to couple with something called spherical collapse. So you have to assume that these halos are spherical. This is an assumption. There is no question about that. But what is the spherical collapse advantage is you can again work out everything analytically. How does a spherical region, which is slightly overdense in an expanding universe, how does that evolve? So it will initially expand with the universe, then it will expand slower than the universe, then at some point it will stop, it will turn over, and then it will collapse. Okay. And in the spherical collapse, there are various nice things which happens. It turns out that a spherical region collapses to a halo when the corresponding linear density contrast, of course, the system is not linear, but suppose you just calculate the linear density contrast by extrapolating the linear theory. It turns out that when the linear density contrast is 1.686 in standard CDM model, I mean, this changes a bit when lambda comes into the picture, but when the value is 1.686, the thing collapses. So basically, you can learn a lot about the collapse just from linear theory and spherical collapse. The actual density contrast can be quite high, of the order of 200. But if you had just evolved it linearly, you should be able to show that at 1.686 it collapses. Given that these two facts, you can work out the
collapse. You mean that's contracting? I mean,
it
starts collapse.
No, it has reached. Okay, so
its maximum, or
no, it has reached virialization. That is often called as collapse. So since you asked, what happens is, think if there is a perfect spherical region, what will happen is it will expand, turn over, and collapse to a point, because it will just go to r equal to 0. But what happens is at some point the non-radial motions start to play a role. So it basically kind of reaches a equilibrium. That's like a virial theorem where potential energy and kinetic energy gets related by the appropriate formula. It's at that is usually called collapse. I mean, the point at which virializes, that is also called the collapse in this language. So it's at the virialization that happens.
So then how do you get, I mean, you are actually running the program presuming that no collapse happens. You're just using linear perturbation theory. And at some point there must be some marker.
Yes.
Which then
yes. That
comes at delta C at 1.6.
Exactly.
What is the marker then?
Marker is the point at which the radius actually reaches the virial radius of the halo.
It does this and
yes, no, this you can, this you can also do kind of analytically. This is done kind of analytically. So what you say is the spherical region expands, then collapses, but I won't go to 0. I will stop at the point when it reaches the virial radius. Let me try to calculate what is the corresponding linear density contrast at that time. It's 1.686. It doesn't depend on anything else, just because of the symmetry in the problem. Now, using these two, you can actually calculate the mass function of the halos, number of halos per unit mass range per unit volume. And it turns out that it is given by a nice, simple analytical formula. It's known as pressure mass function, very popular. Except that, yeah, pressure mass function, yes. No, that is a fit. So you would see Schechter fits to the luminosity function. Those are Schechter fits. So firstly there is no press, and those are fits to the form of the luminosity function. This is an analytically derived mass function, halo mass function. The same Schechter, but this is press Schechter. Okay, the press is another person. So, yeah, sorry, yes. Yes, so this, if you ignore lambda, this can be at any redshift. So whenever at any redshift, it's just that that region of radius r, its corresponding linear density contrast has reached 1.686. So suppose you have one region in the initial condition, which is linear, you evolve it using linear theory, and you find that at redshift 13.6, its linear density contrast will reach 1.686. Then you know this region will form a halo at redshift 13.6 of this mass, whatever is mass in that region. And that region, suppose it reaches 1.686 at redshift 2, then this will form a halo at redshift 2. So this is how it works. It has to reach 1.686. Okay. With lambda, this value changes a bit. Okay. So that's the only details. Small n is the number per unit volume. Then this is per unit mass, basically. And this is formula. But I mean, the story is this is just too simple. So what I have plotted here is these black lines are what you get from simulation. Red is the Preschecter prediction. So you see it gets the qualitative features quite right. Okay, it's kind of power law, false exponentially here. But quantitatively, it doesn't do very well. Particularly at high redshift, it gets quite bad actually. So here you are really making orders of magnitude kind of, yeah, almost order of magnitude errors at this end. So it is a good handle to start with, but really, I mean, if we are really trying to do quantitative analysis, one should not use Preschecter. Then, I mean, people have, yeah. No, so there is no baryons here. This is only dark matter. Only quantity that is involved is the mass of the spherical region, because a spherical region only has one quantity. It's basically the mass. So it doesn't depend on angular momentum or any other things. So those are there. So what people did is then they started to extend it. For example, just instead of spherical collapse, talk about ellipsoidal collapse. Okay, then and so on. So there is a lot of literature in this. But this is something which is also very popular in cosmology literature. This is called Shed-Torment mass function. And that Shed-Torment mass function is showed by a blue line. And you can see that is a much better fit to the simulations. Nowadays, people have much better fits. I mean, Shed-Torment is something we like because it can, I mean, there is analytical motivation behind it. But people will give you fitting functions from simulations, very accurate fitting functions coming from very detailed simulations and so on. Those also you can use. So there is a lot of analytical handles on these mass functions. As I said, this is something which we think we understand quite well. Now, this study of mass functions also give rise to this concept of hierarchical structure formation. So this is again another plot taken from another paper. So you can see these are mass functions at different redshifts. So mass versus number of halos. So firstly, you can see the number of high mass halos is less at high redshifts. So basically, if we are talking about, let's say 10 to the 11 solar mass halos, as redshift 10, you have something, but at redshift 20, you have basically nothing at 10 to the 11. And similarly, you can talk about any mass halos. You will see that at earlier times, higher mass halos are much more difficult to form. So basically what happens is small mass halos tend to form first, and the high mass halos basically form later because the small mass halos essentially merge to form the small mass halos. So this is how the hierarchy goes. There was a time when people did not know about whether dark matter is cold or hot. Hot dark matter, for example, tends to produce the other way around. Okay, it produces large halos first and then they kind of fragment into small mass halos. But now we know that in the cold dark matter, this is what we have to deal with.
Smaller halos merge into forming larger halos. Then shouldn't the density of smaller halos be going down?
No, because
all of them.
No, because more and more halos are constantly, because somewhere else some another halo will form. So no, it is, yeah, it doesn't basically, but that is what happens. Constantly structures are getting formed everywhere. Now, because of this hierarchical structure formation, our kind of expectation is that the first stars are expected to form in relatively small mass halos, okay, because those are the first ones to be around. And that really helps a lot in this warm dark matter or constraining the nature of dark matter, which we'll come to later, but this is the starting point. Now, as I said, this I will go a bit quickly. Then once you have the dark matter halos, you have to do all sorts of astrophysics in that. So you have the dark matter halo, the gas particles will also basically start collapsing in the gravitational potential, and basically it picks up the temperature equivalent to what we call the virial temperature. Basically what will happen is the gas particles will fall into the potential well, and it will pick up energies of the order of the depth of the potential well. That's the potential energy of this thing. And you can convert that potential energy into a temperature. And basically that temperature is very high, of the order of 10 to the 4 Kelvin or even higher. Now at that kind of temperature, you cannot form stars. So what needs to happen is this gas cannot just stay in that heated state. I mean, or if it stays in that heated state, there won't be any star formation. You have to find a way to cool and condense that gas. So how do you cool? This is achieved by something called radiative cooling. What is radiative cooling? Basically, the atoms, the gas particles will collide with each other, and once in a because of this collision, one of the atoms can get excited. The electrons in one of the atoms can get excited to a higher level. So that is just collision. You haven't gained or lost energy. Now what happens is when the atom de-excites, the electron de-excites, it will emit a photon, and if that photon escapes the kind of the halo, then it will eventually lead to loss of energy and hence cooling. So this is the basic idea about radiative cooling. But for radiative cooling to happen, what you need to do is these collisions should be able to excite the atoms to a higher level. So if the initial temperature is not too high, what will happen is they won't be able to cool. So there's this paradoxical situation. You need a reasonably higher temperature to start the cooling. If it is to start with cold, it will just remain cold because it won't be able to excite the atoms to the higher level. So this is the thing. So basically, which essentially means is that halos which are too small will not be able to cool, and typical numbers are 10 to the 8 solar mass, because there the temperature won't be high enough to do this excitation to start with, and temperature won't be low enough to form stars. Okay, so there the gas will just remain in like equilibrium in that and won't do anything. Okay, now this is basically this temperature is determined by the excitation levels of hydrogen atoms. So in case there are molecules, then what happens is the cooling rate can be boosted. So even smaller mass halos can cool because you have access to rotational and vibration levels of these molecules, which are much closely separated. Okay. Yeah.
So if the temperature is higher than 10 to the 4K, you have radiative cooling and falls below 10 to the 4K, then once again it will stop cooling.
Okay, I mean it's slightly more complicated than that. I mean, so basically when it starts cooling, it immediately starts to condense, and then the temperature again goes up. Okay, so all sorts of things happen. So yes, in principle, there could be situations where the cooling stops and you can't do anything. But the ideal situation is it starts to fragment, constantly go on fragmenting, and because you have to form these smaller clouds eventually, and that is how things happen basically.
That can't happen for the gases that are less than 10 to the 4K.
10 to the 4K, the initial that condensation won't happen. That's the problem.
If you cool, you may condense.
If you are not
cool and get down to 10 to the 4K, you may still condense into smaller groups. But if you were started off at less than 10 to the 4K, you won't fragment it.
Yes, you won't even do this initial cooling basically, which is needed for the condensation and fragmentation. So that is the problem. So it is not like a step function kind of a thing. There is a smooth thing. I mean, so above 10 to the 4K, I mean, this will be very efficient, and a few times 10 to the 3K, it will be less efficient, and in the middle. So there is a region where it's gray, I mean, in between. Yes, but these are typical numbers to keep in mind. But so all these physics, I mean, one should try to understand in principle, but at the end, what you probably need is just, depending on the conditions, let us assume that a fraction f star of baryons can be converted into stars. So not all the baryons can go into the stars, because I mean, Raghu was also asking, I mean, not all the gas can cool so efficiently. So this is where we are. And as I said, once you know how much baryons have gone into stars, you can basically find a way to calculate the star formation rate, the mass distribution of the stars, the metallicity and things like that. And using those, you can calculate the radiation from the galaxies. Okay, so I've hidden a lot of things in this sentence because this is really way more complicated than what we can deal with this. And then comes the most complicated part. Yeah. Yes. 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 Nothing else. Yeah. It's just the gravity is dominated by dark. And dark energy does not gravitate, so doesn't play much role. So what happens is, now, as I was saying, not all the photons will escape into the surrounding intergalactic medium. So then we have to worry about this escape of photons, and this is very difficult to model. So for most reionization models, what we have to basically assume that a fraction f escape of photons kind of go out into the intergalactic medium. The f escape can in principle be a function of the halo mass and redshift. Okay, maybe it depends on other conditions, like in what environment the halo has formed and things like that. So we really don't know. But to the zeroth order, this is a fraction, this is a number which we have no control over, and we have to keep it treated as some kind of a free parameter in most of the models, and hope to constrain using something, some reionization observation, some other observations, we don't know. Okay, so this is because of this, yeah, modeling becomes really difficult most of the time. Okay, and I mean, there are very few observational constraints. That's another problem. Now, I will now skip a lot of steps, but under certain approximations, basically you have to make some approximation related to star formation, regarding what kind of stars it has formed and things like that. What you can show is globally the number of ionizing photons per unit time per unit co-moving volume, number of ionizing photons produced, is basically given by the average neutral hydrogen density times time derivative of a quantity which I call zeta times F collapse. So what are these things? Zeta is basically efficiency parameter which hides all the physics which we talked about in the last couple of 2-3 slides. So basically zeta is a parameter which is given by F escape times F star. F escape is the fraction which escapes. F star is the fraction of baryons which have gone into stars. So all your star formation, physics, cooling, this, that, times a number which we didn't discuss. Basically, it's the number of ionizing photons produced per unit mass in stars. This can be reasonably well determined by this population synthesis model. So, and this MP is to make it dimensionless, divided by, because we are talking only about hydrogen, this is 1 minus the helium fraction. So these are just details. So this is the efficiency parameter, which is kind of, it's often called the reionization efficiency or things like that. So reionization models really depend on this parameter.
Proton mass?
Proton mass, or hydrogen mass. Physically, this can be interpreted as the number of ionizing photons produced by the stars and escaping into the IgM per hydrogen inside the halo. I mean, that is how this zeta can be interpreted once you write the proper relation of number of ionizing photons and the halo mass and then things like that. And this quantity, the F collapse, is basically the fraction of mass inside halos above some mass m min. Why above some mass m min? Because remember, lower mass halos cannot form stars, so we should not count them. So they might be halos of all sorts of masses, but for reionization, you are interested in only halos above m min. So you see, this is the number of halos per unit volume per unit mass. You multiply by the mass of the halos. If you just integrate over all mass, this will give you kind of mass per unit volume inside halos, some kind of density. And if you divide by the total matter density, this quantity would have given you the what we call collapse fraction. But then you can multiply this by the zeta as well. If zeta is independent of mass, it will just come out and sit. It will be zeta times F collapse. But in principle, you can keep zeta as a function of m also, because there is so much physics here, so we really don't know. So zeta can go and sit inside as well. So this is this average quantity. So this, its time derivative essentially gives you the number of ionizing photons produced. Yeah. Yes, I mean, it is of that order. What you can do is you can couple it to the virial temperature of the halo. So you can say that the virial temperature of the halo needs to be 10 to the 4 K and above. The relation between virial temperature and the halo mass has a mild redshift dependence. So that you can put in if you want. So those are details. Otherwise, even if you take 10 to the 8 solar mass, I don't think it's going to make a lot of difference to the model, given there are so many other uncertainties. Yeah. Yes. Oh, so DNDM is a time dependent quantity, as you have seen the halo mass function. Zeta we don't know. In principle, it can be a time dependent quantity. And in principle, this min can also be a mildly time dependent quantity. It depends on how well you want to model it. So there are various things. So ideally, you should calculate this at every redshift and calculate the derivative numerically. Yeah, that's how we do.
It's a per hydrogen inside the halo, that hydrogen either in stars or in ions.
Yes, total hydrogen inside the halo. Yes, yes.
It's more in stars than ions.
No, because how much is in stars will be taken care of by this F star parameter. Typically 10%, few percent are in stars.
There is more in the stars rather than the ions.
No, it's the other way around. 10% in stars and most in ISM. Yes. I mean, it depends a bit on, I mean, lower redshift, the star formation efficiency is slightly better because of all these molecules, the cooling is helped. At higher redshifts, they are much poor because only hydrogen is there, which does not allow too much cooling of the gas. But that's typical. Okay. Now, if you remember that block, we have done about, we have discussed dark matter halos, and then we have discussed all this radiation happening inside and the formation of galaxies, radiation, and also the escape. Okay. Now, so this tells you basically the source of reionization, how many ionizing photons you have produced per unit time. Now you have to do the radiative transfer to see what happens in the surrounding intergalactic medium. So basically, in this case, let us assume that the locations of the sources and the luminosities are known. Luminosities are known because we have just modeled it in the with all our simplifications, we have modeled it in the previous slide. And locations we know, suppose you have run a simulation, so you will know where the dark matter halos are formed, for example. So what you need to do is you need to solve this, what we call the radiative transfer equation, and work out how the radiation basically propagates. So the crucial quantity in this case is what is known as the specific intensity. And that specific intensity actually satisfies this very complicated equation. People who have done radiative transfer somewhere will realize the first two terms on the left-hand side and the terms on the right-hand side. So this basically takes into account the absorption, this is emission. And these two terms comes because you are working in the expanding universe. So you see this Hubble parameter appearing. So this is the redshift term, this is just the volume dilution term. Okay, so in principle, you need to solve this 7-dimensional partial differential equation. And people who have tried their hands with numerics will realize that this is kind of impossible to solve in general case. It's just the dimensionality is just too high. It's not possible to solve with the current computers. It's not going to be easily solved even in the near future with at least the standard differencing schemes. So basically, people who run radiative transfer simulations will make some simplifications in this equation. Either they will assume some symmetry, or they will take moments and convert this equation into some kind of equations of kind of fluids. It's a radiation hydrodynamics, that's what they call. Okay, or they will, instead of working with this continuous field, they will kind of decompose it into rays. Okay, what we call characteristics of this differential equation. They will trace those characteristics. So there are ways to do that, but all of them are assumptions, and depending on the assumptions you put, your results may change. I mean, many people do radiative transfer, full radiative transfer simulations, and not all of them agree with each other. It depends on what you put. Okay. Now, what you can show is that, suppose I'm not really interested in how this radiation goes. I'm not interested in all the frequencies and so on. I just want to know how many hydrogen atoms are basically getting ionized. Okay, so I really don't care about any other wavelengths and other things. So if you are really interested in that part, this equation can be simplified quite a bit, and that led to development of semi-numerical methods. Okay, so again, I won't have time to go into the details of how these semi-numerical methods come into the picture. But essentially what happens is you can show that this equation kind of reduces to something which looks much simpler, basically, where you are just counting the number of hydrogen atoms ionized compared to the number of photons produced, and you get some kind of this kind of picture. So what is shown here is a result from one such semi-numerical model which we have been working on. It's called script. Now, what is these are basically simulations, and what we are showing are slices, two-dimensional slices in a 3D box. So what has been shown here, the left-hand side are basically the density field, and you will see as the time evolves, this density basically, the contrast basically grows, and you will see this cosmic web appearing. And wherever the densities are high, places like here, for example, you will see these white dots appearing, and they are like the possible locations of halos and hence galaxies. Okay. So this is how basically the structures evolve. So you see all these halos have lit up at some point. Now this is basically the same slice, but now showing the neutral hydrogen distribution. Red one is neutral, black one is ionized. Initially, everything was red, and you see all these black regions appearing, and then they are growing, kind of overlapping with each other, and then the whole universe gets ionized. So this is how reionization progresses. Not only that, the black regions tend to appear first around where the galaxies form. For example, you can keep an eye on this region where a lot of galaxies are forming. Hence, the neutral region forms, and then there are other galaxies, and then they come and merge. And if you keep an eye on the voids, you will see those are the parts which will become kind of, they are devoid of neutral hydrogen to start with, but they will become black towards the end, essentially. And so that is why one thinks that studying reionization will help us in learning about the first galaxies in the universe, because where the neutral, the ionized regions form will be kind of tracing the underlying dark matter distribution or the distribution of halos. And mathematically also you can show that there are kind of close relations between these two. So that is why people think that reionization will help in understanding how the first stars form. Now there are other complications while modeling, and that has to do with feedback. And that's something I talked a lot in the morning and then during the question and answer session. So we already showed that if the gas cools by atomic transitions, then the minimum mass of halos which can form stars is of the order of 10 to the 8 solar mass. Presence of molecules can take you up to 10 to the 6 solar mass, but whether molecules can form in the early universe itself is a question mark. Okay, so there is a lot of controversy there as well. However, there could be feedback effects, and that can affect the value of M min. One kind of feedback is called radiative feedback or reionization feedback. Basically, when reionization happens, that also leads to heating, because the photon will come, knock out the electron, that excess energy, the electron will transfer into the gas basically, and the gas will heat up. Now, if there is heating, what will happen is the small mass halos, if the gas heats up there, because the small mass halos have lower potential energy, the gas can acquire enough kinetic energy to just come out of that halo, and then you cannot form stars there. So the halo is there, but there is no gas in it. Okay, and this will preferentially affect small mass halos because large mass halos have a lot of potential energy. It's not very easy to just give a little bit of kinetic energy and expel the gas from there. Then there is something called mechanical feedback. For example, supernova explosions can deplete the gas from shallow potential wells and hence small mass halos. So you can see small mass halos are always in a disadvantage. They are the ones which will form stars first. And because they form stars, their star formation will get affected. So it gets killed. So there is a kind of regulation, it seems, in the nature. Okay, so you have the small mass halos. Now, suppose you say that I want to do reionization very fast because of some reason. So you make it very efficient, you make them form stars very efficiently. What will happen is you will eventually make these feedback processes also very efficient if you do the physics properly, and you will start killing them. So it's not very easy to do reionization the way you want all the time. There is always this regulation, which, I mean, there's freedom in that regulation, but you really cannot do whatever you want. So that is something which is nice. There's something also called chemical feedback. What happens is the initial set of stars will form in an environment, in a gas, which is predominantly hydrogen and helium, because no other higher element formed in substantial numbers in the early universe. Okay. Now, what will happen is, where do all these higher order, what we call metals in astrophysics, form? They form inside the stars once these nuclear burning starts. Okay. Now, these metals, what can happen is these stars, if they have in the end stages, they go into supernova and it explodes, that metal can be distributed into the medium again. So next generation of stars are forming in a gas which is not only hydrogen and helium, but there are other elements as well. So the cooling processes are different, hence the nature of the stars are different. The first generation of stars, because of historical reasons, are called population 3 stars, and the next generation of stars are called population 2 stars, and that transition happens, and that changes many of those factors, those F stars and F escapes and etas, and so hence that efficiency parameter can change because of this transition. Again, very difficult to track this because it's so complicated, but all these feedback processes happen. So this is about basically reionization modeling. Let me quickly go to, suppose, I mean, you have modeled it, then what do you compare with? You can compare with Lyman alpha absorption, so which again, I don't have to repeat, but if you have a quasar, there will be Lyman alpha absorption like the Lyman alpha forest, except, so this Lyman alpha forest is very useful in understanding that reionization has happened. So what happens is, these are basically Lyman alpha forest across a wide range of redshifts. At lower redshift, you see almost no absorption, okay, because really almost all neutral hydrogen has been depleted. And then this forest-like structure appears. And then you go to higher and higher redshift, then you see it's very different. Like this is a standard Lyman alpha forest picture. Here you see it's mostly all absorption. Here, basically, it's mostly transmitting, and there are only a few absorption features. Here, it is mostly all absorbed. Okay, so the nature of this Lyman alpha forest really changes. Now, if you do the calculation, what you can show is the transmitted flux is basically the observed flux divided by continuum. We have some idea about the continuum. So, given the observed flux, we know what the transmitted flux would be. And theoretically, this transmitted flux is given by exponential negative of optical depth. And if you work out that optical depth, it will turn out to be of the order of 10 to the 5 times the neutral hydrogen fraction. H1 stands for neutral hydrogen, basically. H2 is the spectroscopic notation. H2 is ionized hydrogen. But this is the kind of numbers you have. Now you see, even if the neutral hydrogen fraction was something like 10 to the minus 4, you would get a tau which is 10, and e to the minus 10 for all practical purposes is 0. Okay, so which means the fact that this is not 0 here means that the neutral hydrogen fraction is of the order of 10 to the minus 5 or less. So that is why we know that up to redshift 5 or so, the universe is highly ionized. Otherwise, we won't see anything here. It would be like consistent with 0 all throughout. Okay, so that is how Lyman alpha forest tells us that universe is completely ionized at these redshifts. Yeah.
Lyman alpha has a very defined wavelength.
Correct.
And the reason we see a forest is because we are observing the Lyman alpha radiation at different.
The absorption at different redshifts.
Then, I mean, how do we see a different forest at every? The forest itself was a different of.
No, what do you mean? Why do we? So this is, for example, this is a quasar at redshift 0.15. So what you are observing is the matter between 0.15 and 0. Whereas this was, for example, a quasar at redshift 2.4. The matter is between 2.4 and us. Okay, so you are. So this is all. This is there is a redshift effect here. Okay, so you're actually observing everything between the quasar and us. Quasar, yes, correct. So this thing is happening at a redshift lower than that. Correct. So this would be that corresponding redshift, and yeah, anything lower than that, we will see that. So that is why one needs, if you want to study Lyman alpha forest at higher redshift, you have to look for a quasar at a redshift higher than what you want to study. Absolutely. So these are tracing the neutral hydrogen density fluctuations. So most likely wherever you see almost no absorption is probably a very underdense region, void. Okay. So there is hardly any neutral hydrogen. And these are probably somewhere in the filaments or crossing a filament or something like that. And that one can figure out by looking at the simulation. And once in a while, these are not present in these plots. Once in a while, you will see a strong absorption, which means the line of sight has passed through a galaxy or outskirts of a galaxy. So everything gets absorbed there. So those show up very prominently. Those are known as damp Lyman alpha absorption. Okay, so this is the basic idea. So basically all these plots up to redshift 4.76 and of course still up to around 5.5 is telling you that universe is kind of ionized there. Otherwise, this would look very different. You are finding that the flux is almost consistent with 0 here. I mean, but then even if it is 0, it basically means that neutral hydrogen fraction is above 10 to the minus 4. So it can be 10 to the minus 4, it can be 1. It's not telling you much. Okay. So that is why Lyman alpha forest tends to become slightly more insensitive as you reach the higher redshift. However, what happens is around these redshifts, then you have to go through simulations and modeling. Okay, so there is, I mean, just by looking at this seems consistent with 0, but then you see some regions where there are spikes and things like that. So now if you go and try to model it carefully and you have to assume some reionization model and things like that, you can probably put some constraints. But that will be very model dependent and how well you can simulate this Lyman alpha forest. So this is basically one way of constraining reionization. It's roughly telling us that reionization is ending somewhere between 6, 5.5, depending on what kind of models you have and what kind of data you are dealing with. So that is one part of the picture. We know that reionization was completed somewhere around 6, 5.5, something around that. These ones. So as you reach lower frequencies, you are probably hitting lower redshifts. So probably you are hitting things where the ionization is more. So it starts showing up there. No, but okay. What happens is beyond a point, then there are other problems, because beyond a point, you will be contaminated by, for example, Lyman beta transitions, which starts to appear somewhere here, and Lyman gamma and so on. So it's not very easy to interpret the observations. And at some point, I mean, it's not like one telescope you will be able to observe the whole frequency range. And then, this flux will also slowly go down, the quasar flux. And so basically at some point you will be able to see anything. So there are various observational effects which you have to account for. So one cannot really go to arbitrarily low frequencies in just one quasar. So that is, the thing. So a telescope which is observing this redshift 6, the way you have chosen your frequencies and other things won't give you, spectra till redshift 3 or something. But then you have to change the observing strategy for that. So now we have talked about studying reionization using neutral hydrogen. All this is happening because of Lyman alpha transition of neutral hydrogen. There's a complementary probe where you are probing not the neutral component of the universe, but the ionized component of the universe, and that is through CMB. So CMB, the photons are coming towards us. So photons are essentially free streaming. Now, the moment you ionize the universe, you produce a lot of free electrons, and the CMB photons can start scattering of those free electrons, and that will show up as an imprint in the CMB spectra. Basically, this scattering is Thomson scattering. It has an angular dependence, and as a result, it can distribute the angular pattern of the CMB. See, CMB, all our information is coming from the angular pattern we see in the sky, all these angular power spectra and things like that. That starts to get changed. Okay. Not only that, because of this angular dependence, it can give rise to polarization as well. So there will be a polarization signal. The quantity of interest is basically another optical depth. This is the Thomson scattering optical depth. So you can see is a Thomson scattering cross section times the path length, which is CDT, times the number density of scatterers. In this case, it's the electrons. And you have to just convert from co-moving density to proper density and things like that. Now, what happens is, how do you, the thing is, CMB observations are likely to give you the value of this tau, which is the integrated kind of effect. Remember, if reionization did not happen, then the density of density of free electrons will be 0 and tau will be 0. If reionization happened too early, then this integral will be contributed by a large kind of wide redshift path, and hence tau will be higher, okay, and so on. So just from the value of tau, you can try to infer about reionization. Tau is also strongly degenerate with the amplitude of primordial power spectrum. So it has implications for cosmological parameter estimation, but that's another story. And that is why you will see all the CMB, this parameter estimation will have tau as a parameter. You cannot do without tau because of its degeneracy with cosmological parameters. Now, this tau measurements has a long history basically. So when WMAP came out, in fact, in this plot, what has been shown here is the tau constraints versus different experiments. It starts with WMAP 3 years because WMAP first year put it at a very large value, and hence there were a lot of activities in the community thinking that, okay, reionization is so early, POP3 stars, very efficient, this, that, all sorts of things happened. Even we got involved in various exotic theoretical models. With WMAP 3 years, you can see tau value is of the order of 0.09. Okay, so of the order of kind of 10%. But it turned out that even that is higher, because by the time Planck came up, you can see the values have actually gone down. So because of Planck, we now understand that reionization occurred much later compared to what we thought during the WMAP days. Okay? So this is an example where our understanding of the process is entirely determined by the observation. So if tomorrow the tau value changes again, unlikely, then again we have to revise our reionization models. No, I saw you first. So this is a, yes, this is a globally averaged quantity. There are tau fluctuations also, but it is so small. There is information there as well, but you cannot do with present. No, it is slightly more than that, but this detecting this tau itself is a challenge. Okay, it's not a very prominent effect. It's not like CMB angular power spectra. But in principle, through polarization, but at the tau fluctuations occur at much smaller scales, which is large L values. There are other challenges there, but with future experiments, one can do that. These are some studies we are also doing to see how you can use tau fluctuations to constrain reionization, but that's really far future. So, yeah. Yes, so CMB, you have this, you see this anisotropy. So this is something which is happening at the last scattering surface or just before that, and it also has imprints of what is happening between the CMB and us. So those are called secondary anisotropies, and both are there. Okay, things like integrated Sachs-Fulda effect and other things are secondary anisotropies. Similarly, Sunyaev-Zeldovich effect, and these are happening at lower redshifts, right? This is one such secondary effect, and we are observing just one CMB, which is primary and secondary all coupled, and because of that, this tau gets entangled with other cosmological parameters, the inference about other cosmological parameters. Yeah. So what tau does is dampens the temperature anisotropy at all L values, because so some e to the minus 2 tau. But that you can compensate by just increasing, let's say, AS, the amplitude of the power spectrum. So that is the degeneracy. But tau also produces polarization, which cannot be mimicked by anything else. So that is how the degeneracy got broken by W map, and then with Planck. So if that did not happen, we would never be able to constrain tau. We will only be able to constrain AS times e to the minus 2 tau. You would see this parameter appearing in many of the CMB papers, because that's very degenerate. Yes. Yes. What we observe is whatever is produced at the time of decoupling and whatever happened in between. Everything is imprinted because we are observing here. Yes. Yes. No. That has everything. No, they cannot. I mean, you have to do a parameter estimation to subtract. So it has the tau put in. Yes. So if you, yeah, exactly. Yeah. Yes. Most likely, yes. Compared to what we thought during the WMAP days. Yes. Yes. Okay. So I think it's too early. So it depends. Now, if you're talking about the galaxy at redshift 10.6, that probably, I mean, I don't think it's a really problem for lambda CDM. You can have slightly different galaxy formation models and produce it. There are some difficulties in producing some of its properties. That's what I understand. But it is not a disaster. But then there are other galaxies claimed at much higher redshifts. Now, those are not spectroscopically confirmed. Okay. And let us wait for some time for them to get confirmed. Okay. And let us also see the population a bit. Okay. So I think it's just too early. I mean, I will just wait for some more time before concluding anything about those. Okay. Now, what we can do is, now you have this tau measurements, you have this Lamin alpha forest measurements, you have to do some statistics. What in principle one can do is you can actually make analytical models and try to kind of constrain all the cosmological parameters along with, I did not show, the reionization parameters. So you vary everything. You take the Planck likelihood, you take the reionization, the Lamin alpha forest measurements, You throw in everything and do a full MCMC, just like the CMB community would have done. But here you are adding a reionization model as well as the observables related to reionization. And what happens is, what I've tried to show, let me go to this plot, for example. So green, remember, is only CMB, like the conventional CMB analysis. And the other one is where I add Lyman alpha forest constraints, like reionization modeling as well. So what I was, this is tau. These are some parameters related to the power spectrum. So you see, without the reionization constraint, reionization observations, this is the kind of constraint you will get on tau versus AS, the green one. The moment I put reionization constraint, what happens is your tau starts to get constrained very well, because there is some reionization history which will be preferred by the Lyman alpha forest and other observables. As a result, your constraint on AS also improves. So the moment you put in reionization observables, your constraints on cosmological parameters improve, in particular those which are related to the power spectrum. Okay, and that is basically very good use of reionization observations for doing cosmology, and that gave us hope that one can also try to probe like anything which affects the power spectrum, like dark matter. Yeah. Yes. Purple, okay. Purple curves is where we also put the forecasted 21 centimeter data, which I did not want to talk about, but I talked about in the morning's lecture. That, no, purple, you see, it makes it slightly more stringent, right? It is smaller than the blue. The reddish one, right? Oh, okay. So let me take a step back. I forgot. This is my mistake. Green one is only CMB. Okay. Did I make a mistake? Maybe I made a mistake here. Okay. So basically, the blue one is. Oh, this is correct. So blue one is along with 21 centimeter. It relaxes the constraint because of a very peculiar region. And this is not forecasted. So I take it back. It is with the ages data. Now the problem is, now you would say, why would adding some data set will relax the constraint? Because to match the ages data, what we need to do is we cannot do with one population of stars. And not only that, we have to introduce all this radio background and things like that because of its long dip. So the model has more free parameters. As a result, it basically relaxes other constraints as well. I'm happy that the edges result is probably gone, okay? Because otherwise, we are going nowhere with that, unfortunately. Yes, and that is the next point I was trying to make, that with Lyman alpha and CMB, you can do a lot. But if you want to do more, you have to go to 21 centimeter radiation, 21 centimeter signal. And there's a lot of activity going on. There are a lot of telescopes trying to detect the global signal. There are probably many more which are trying to detect fluctuations, but these experiments are much more expensive than these. But these telescopes are also much more general purpose. And this is the global signal. It has a lot of features. Let me not try to go into it. This is something which is the most prominent feature, and that's something the global 21 centimeter community first tried to detect. The edges claimed a detection, but it was very controversial. And basically, we think that it's probably being ruled out by the SARAS experiment. So this is a picture of the SARAS experiment, which is on a water. I think Saurabh will give a talk, right, in this conference, if I understand. So he will probably tell a lot about this aspect. Now, what we did was, let's not worry about edges or anything. Let's say that in the future, there will be some 21 centimeter detection in the global signal. So we took some specifications of a future experiment and tried to add basically that. And here we get what we expect. The moment you add future global 21 centimeter data, you see that whatever we were getting with CMB plus reionization observables, we get something which becomes much more better. So with the upcoming 21 centimeter data, we will have better constraints not only on reionization, but also on cosmological parameters. So that is basically the hope. And again, you see, we have varied here all the cosmological parameters and some parameters of reionization and other stuff. And in principle, now you can say that I will relax my ΛCDM model and put in warm dark matter. So this code can handle everything as long as you can do things analytically. So this is basically what it shows, that with the future data, you will do much better in constraining these models. This was about global. Now it turns out that if you go to fluctuations, you can learn a lot more. Now what I'm trying to show here is another movie from our code. Now this is something which I showed earlier, these bubbles forming and growing. Now suppose I want to measure the fluctuations. The fluctuations are best measured by the power spectrum. So this is the power spectrum of H1 versus the K. And remember, these are the same, the large scales, these are small scales. And you see, as the reionization evolves, as these bubbles form, grow, merge, and things like that, this power spectrum starts to do funny things. Okay, I mean, it initially remains the same, I mean, not changing much. Then it changes its shape, then it will go up, become flat, go down, and then it vanishes because everything gets iron. So there is a lot of information in this. For example, this peak roughly corresponds to the typical bubble sizes we will have, just to give you an example. Those bubble sizes are determined by what kind of halos host the first stars, and so on. So there is a lot of information in this. What we can do is, rather than studying the power spectrum in one redshift, what you can do is you can try to study the power spectrum as a function of redshift. So take one typical scale which is of interest, like here, and plot it against a function of redshift, which means against a function of frequency, because just redshift will just transfer into frequency because we are talking about a line transition. And that also does a lot of interesting things. In particular, what is interesting is this peak, which appears around the time when the universe is roughly 50% ionized. So if we can detect this shape roughly, in particular this part of the shape where it peaks and goes down, it will give us an independent handle on when reionization occurred and when reionization was 50% and it died down. So that is basically one target of these experiments, these huge interferometers. They will try to do that. Now, the thing is, it is probably not going to happen with the interferometers we have at the present. Interferometers are nothing but these arrays. We have to wait till something next generation comes up. And there are kind of a couple which are really going to change the field. One is the SK, in particular SK law, which is coming up in Australia. SK law is very interesting for us because India is going to be a partner in the SK. We were involved in the SK in the design phase, and we are going to probably join the construction and the operation phase as well. So we will have access to this data in some form or the other. And hopefully SK will not only make a detection, but also allow us to constrain all these models which we are talking about. There is another telescope called Hera, which is kind of built, and that also will have sensitivity comparable to the SK, and we'll see. I mean, probably if this one comes up earlier, this may also do something very interesting, but both have their advantages and disadvantages. So we really don't know which one will reach there first. The present status is shown in this plot, where we show the present constraints on the 21 centimeter power spectrum at a particular value of K, which is that typical value which I chose by showing the movie. And these are the kind of numbers we have from different telescopes. So what you see is, in fact, the first kind of upper limits were put by GMRT. in 2013. The plot is, I think, it is somewhere here. But then all other telescopes, which are probably much better suited to detecting reionization, started to do much better. And some of these upper limits, which we see here, are coming from telescopes like MWA, Hera, that partially made Hera and LOFAR, basically. However, these numbers are still much higher than canonical reionization models. So you can see they are orders of magnitude higher because we haven't reached that sensitivity. Hopefully, what will happen is current telescopes with kind of 1,000 hours of observations will only be able to rule out extremely exotic kind of outlier models of reionization. They may not be able to go and detect this signal, which this is a typical signal which we expect. That will probably be done by SK, even with the 100 hours of observations with the SK. It should be able to detect and probably start to do parameter constraints. SK with 1,000 hours will probably be able to image that thing. I mean, you will be able to see bubbles in the sky. But it is an extremely challenging experiment because the signal is very weak and it is hidden under all other astrophysical signals from all sorts of galaxies, our galaxy, and so on. So this is where we are, and the hope is that we will reach this thing at some point. But yeah. But just to, yeah, sorry. Yes. Correct. There is a lot of degeneracy there, yes. So it's not very easy. So you have to understand a bit of reionization and galaxy formation if you want to really constrain some of the dark matter physics. Galaxy halo connection, okay, I have to go back quite a bit, but galaxy halo connection is here. That zeta parameter. This one. So this zeta basically encapsulates, so this allows us to kind of find out how many galaxies have formed and how many photons they have produced, given how much mass is there in collapsed halos. Yes. In principle, yes. It is important because it will tell us what kind of galaxies have formed stars and so on. First of all, you have to predict it at high redshift because often extrapolating something from low redshift can be misleading. Second, you still have this unknown parameter called escape fraction, and that's what I've been harping on. It is probably still possible to do modeling of star formation inside halos. Modeling escape fraction is very difficult. So modeling of star formation will give you everything except the escape fraction. This how much fraction of baryons is in stars, how many photons they have produced, and so on. But then what do you do with that unknown parameter? No, it is more than that. It's just the first thing, but how are they distributed? So because they will be distributed in a very clumpy manner, and depending on how much low density like passages or these tunnels you can create will allow photons to escape easily, and then it can be affected by feedback processes as well, which can like throw away gas and create like pathways for the photons to escape. It's very complicated in that sense. Yes, yes, that is the hope. Yes, that is the hope. But if we are really thinking about dark matter, then you have to do it consistently because all the constraints we'll get on these parameters we would assume CDM, lambda CDM to be the correct model. Okay, then you cannot then take these numbers and fix them and then start to constrain dark matter. That will be completely wrong. Okay, so you have to do it simultaneously, and that's a challenge. Yes. Yes, in principle, it has gotten hidden into this F star eta gamma. I mean, we really, yeah, it is there basically. Though we don't take the relations of Banerjee, we actually take relations which are more free than that. We take some, let's say we'll take some power law relations, but we'll keep the power law exponent free. Banerjee will give you a power law relation. Yeah, I mean, suppose I'm still with CDM. I mean, I, for example, don't trust their things like 100% beyond some redshift. Okay, there is a lot of extrapolation there. There is also a lot of modeling involved in some of the semi-analytical models. So it depends on what you believe. Since we are dealing with models which are fast, semi-numerical, and our approach has been to constrain the parameters, we tend to leave many things free and let it be constrained by, and then try to compare with as many observations as we can, and let it get constrained. Okay. Yes. Okay, I didn't go into that. Even with 100 hours data, I mean, we still don't know how we'll deal with it. I mean, it's not very easy. No. So see, SK is a very complicated beast. So what the plan is for reionization detection? We have now a global community of scientists, and most likely we will try to access the data ourselves, because the data which will be given to other people for usual science won't be appropriate for reionization. We have to do a lot of kind of massaging of the data. So there is a likelihood that the reionization community will find a way to store that data on our own and do our own analysis on our own time. Some initial, maybe the time resolution and frequency resolution, some coarsening may be done live, but there's no way we will do analysis. The analysis itself is a big thing, because we have to remove the foregrounds and other stuff. So we have to find a way to store the data and do the analysis later. Okay. And that is why the requirement of the reionization community will be very different from the rest of the community. And that's something we have to now find a way to deal with the SK community. We don't know.
How did the sky get surveyed? The ground-based telescope.
Yes.
It looks at some part of the sky. If you go around.
Yes.
You see some spot of the sky.
Most of the time, okay. So it depends. I mean, so typically SK will have a few tens of degrees of field of view, because these dipoles, I mean, think of a dipole, it can actually take things from all sorts of size, but you don't want that. So you will do some beam forming and things like that. So it will still be a large. And in principle, we can do cosmology just by looking at that patch of the sky, as long as it is cosmologically representative because of statistical homogeneity. Now, these things are also under like discussion. We may just leave the telescope looking upwards and let the sky pass by. So that's called drift strategy, and then just do analysis with that, because statistically the sky remains the same for cosmology. Or we can also do tracking. We will track one portion of the sky constantly. So all these things one has to discuss and find out what is the best strategy, and each of them have their own advantages. But we never plan to survey the whole sky for these things. It has to be large enough that it is cosmologically represented. That's all. Yeah. So
there'll be enough quasars in that piece.
We don't need quasars for the 21 centimeter, right? We don't need quasars. That is for the Lyman alpha. For 21 centimeter, the background light is CMB, which is anyway coming from all sides. It's the CMB photons which are getting absorbed and emitted. We have to contrast it with CMB. So that's an advantage. Yeah. Yes. Yes. So initially it is just following the dark matter, and that's not evolving seriously. Then at some point, what happens is, see, fluctuations means the contrast between the high density regions and low density regions. Now what happens is the first set of stars will form at high density regions. They will ionize the surrounding medium. So the first places which will get ionized are the high density regions. So initially what will happen is you will decrease the contrast, because where there were more neutral hydrogen, you have cut off those neutral hydrogen. Where there were less neutral hydrogen, you have kept it. So the contrast goes down. As a result, the power spectrum dips. Now you start forming these bubbles, and these bubbles are basically sources of fluctuations. And hence the things start to grow up. And this is driven by essentially the formation of the bubbles. And that will be more when the bubbles, I mean, it starts to go up, but it cannot go up indefinitely, because once the bubble overlap and kind of percolate into the whole medium, then again the fluctuations go down, because you have, it's, everything is kind of the same again. So that is how this shape comes into the picture. Okay. Yes, so I will then quickly just again repeat what I talked about in the morning. So the idea would be to try to detect suppression in this dark matter power spectra. If we are not okay with that thermal relic swarm dark matter, I mean, whatever model you have, if it does something to your small scale power spectra, in principle, there is hope that it can be kind of studied with the observations I was talking about. For example, people have talked about, I think, dark radiation, which produces oscillations at these scales. So even those could be interesting to study. And as I said, those lead to kind of suppression in halos, particularly at small masses. And one can try to do it using galaxies, but that's very difficult because of the feedback effects. But what we can do is we can use a hierarchical structure formation, where what happens is basically you are forming halos, large halos, by merging small halos. So this is a cartoon which shows, suppose initially you have two small halos which form first, then they merge and form a slightly larger halo, and then again you form larger and larger halos. Now if you form two small halos which are much smaller, they won't form stars, because you need a halo of certain mass and above to form stars. So let us say these two did not form stars, these ones did, and then these two merged and form stars here. So roughly this is how things go. So you cannot form stars much earlier, because there the halos would be too small, and too small halos, the halos are there, but the gas cannot cool. The moment you go to something which suppresses small halos, what will happen is none of these halos will form. The halos won't be there. As a result, the first stars will occur only when these halos start to form. Hence, the formation of first stars, which was much earlier in this CDM, will be delayed. And that is basically the idea. Your reionization gets delayed, everything gets delayed, all your signals get delayed, and so on. And that is what we tried to do using edges, but since edges is not probably correct, so this is something which remains open question. But with future 21 centimeter data, one can do a lot. So I didn't want to go much more than this, but I just wanted to give you a future outlook of where that field stands. So global 21 centimeter signal in principle can be useful in constraining the mass of dark matter particles. Also, the 21 centimeter fluctuations can also be used for understanding the nature of dark matter, but I didn't go into the details of how that can be done. But I think we have to wait for HERA and SK to do this, because you need really high signal to noise signals for this. Basically, the challenge is to disentangle the imprint of dark matter from other astrophysical effects, and that is the challenge, and that is something which we have to figure out. Also, when we try to put constraints on dark matter, one has to worry about degeneracies with other cosmological parameters. Now, this is very challenging, because you have to then run many simulations with different cosmological parameters. Now, with all this machine learning and other techniques coming in, things might be easier, but it's still a challenge. So I think there is a lot of work which needs to be done on the theoretical front. A lot of work is going in the observational front. But this is something which fascinates me because there is a lot to be done. And I think this will be a good place to stop. And yeah, if you have further questions, I can take this. Yes. 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 So imagine a region, let's say in this case, a spherical region. So what happens is a spherical region initially will have a small density contrast because at earlier times density contrasts were very small in any case. Now what will happen is this, since this is slightly underdense, let us say, it will attract more matter and it will become more and more underdense, and it will start expanding slower than because there is gravity which is attracting, and then it will decouple from the expansion and it will collapse and it will go to a very high density state which is of the order of 200. That is the actual situation. Okay. Now suppose what I do is I take the linear perturbation equation and just keep on solving that, even knowing that linear perturbation has failed, because linear perturbation will fail down the moment density contrast becomes of the order of 1. But I don't care. I just keep on solving the linear perturbation equation. It just turns out that if you just blindly do that, in that region, when the linear density contrast hits 1.686, that is when the halo gets formed. Here I can do that because I'm tracking, I can track the actual evolution because it is spherically symmetric, and I can work out the linear perturbation theory as well. And that is how we get there. This cannot be done for any arbitrary perturbed regions. So that is what it is. So linear perturbation is not the actual thing. It is just, I'm just solving it using linear perturbation theory. This is all, yeah, this is all, we are talking about dark matter halos, so only gravity. No, stars will anyway, stars won't really affect the formation of dark matter halos because dark matter is the dominant gravitating component. I mean, that is just like 10% of that total amount. They are not going to, so the dark matter halos will form and the baryons will, the gas will just follow that. I mean, will get attracted to the dark matter halo. What do you mean at, because these are, I mean, these are really non-relativistic fluids, okay? I mean, you really don't worry about strong interactions in a river or in the atmosphere or in the ISM. So these are not, I mean, these are really low density gas. At best, yeah, I mean, which will eventually form stars. Once you form stars, there will be other effects which you have to worry about. But before that, you don't have to worry about. I mean, this is just a simple Newtonian fluid. Yeah. Let me take that and then. Yes, okay. So what is usually done in cosmological simulations, you have to, because your initial conditions, you have to put some initial conditions. Those are set by linear perturbation theory because that is what we know. Now you have to start at a redshift where linear perturbation theory is valid at all the scales you are interested. Typical simulations which we run, it is sufficient to start around redshifts of 100 to 50. 50, between 50 and 100. It depends a bit on what kind of scales we are probing, but these are, if you need a typical number, that's the typical number. So you really don't have to go to 1000 and you should not come to like 10 or 20. That could be very risky. So that's, yeah.
Sir, in one of the later graphs where you have this 21 centimeter global signal.
Yes.
So you show a dip in the signal at around, when you said around when the universe is 50% reionized, right? One of the later ones.
No, which global? So
okay, maybe.
So this is the global signal. You are not talking about
not this one, not this one.
So global signal is the one which is sky average.
Oh, right.
And the other one is the fluctuations.
Yes,
that's
this
the
one.
power spectrum.
Yeah, this one. Yeah, sorry.
Yeah.
Yes. So here you say that when it's 50%.
Roughly
Yeah.
50%.
So it has a sharp fall. So why is that?
Okay, so because fluctuations are measure of kind of, I mean, this power spectrum is a measure of fluctuations or inhomogeneities. So when you are forming like bubbles, you have some places where it is like neutral hydrogen fraction is 1, some places it is 0. So high contrast, and it grows once the bubble grows. But at some point the bubble starts to overlap, and then everything is going to 0, and then the fluctuations start to die down. Okay, so there is a sweet spot somewhere between 40 to 60%, depends on the model, but roughly when it is 50-50, and imagine the contrast to be the max. Yes. Yeah.
Hello. Yeah, first question is, so basically you have this bubble of neutral hydrogen and then bubble of
Yeah, mainly bubbles of ionized hydrogen,
ionized
and
hydrogen.
everything else is neutral. Yeah.
And then when they are growing, and then there will be a collision of bubbles.
Yes, they are
Do-
merging.
Do
yes.
people talk about the gravitational wave coming from that bubble collision? And
No, I mean, there's nothing physical, right? It
Nothing.
is just that ionization front is moving. So particles themselves are not moving. I mean, it's just that you have neutral hydrogen, it looks like something is moving. It's the radiation field which is moving. Particles are where they are. They are going from neutral to ionized, basically. So there is no, yeah. So
okay, so another question is, it's not related to this one, is do people talk about the modified gravity model to, specifically in the context of dark matter?
yeah, I haven't seen any modified like MOND models or anything, or even modified gravity models in context of reionization, because as I said, currently the effort is to understand the reionization to start with. But in principle, if simulations can be run, it's, I mean, in principle, there is no problem.
The reason I'm saying, because you are talking about dark
Yes.
matter halo formation, but if you are talking about modified gravity model where there is no such dark matter,
Yes.
but it is just because of the
Newtonian gravity getting modified, or the gravity is
yes,
modified.
So
small
then
acceleration.
your halo formation physics will be completely
Yes.
different.
What had happened was for MOND, for a large amount of, I mean, for a long time, there were no relativistic theory of MOND. So it was very difficult to kind of implement things in these simulations. We didn't know how to calculate the power spectrum and how to set up the initial conditions. But I don't know the status now. But yeah, if this kind of simulations can be set up and run, it will be interesting to see what happens. But I don't know of any group seriously pursuing that in the context of reionization, at least. Yeah. Yes.
So when we go to the standard textbook, for example, Ribicki and Lightman,
Yes.
we don't find the second term. So third and fourth are due to expansion. I get that.
This one.
Yeah, this one. Or is it hidden somewhere? Like I'm
It
not
is
sure.
there. So these two terms combine and give you the di nu ds, basically.
Oh,
I don't know, you have seen
Yeah,
probably that.
optical depth. So
No. So it depends where you started with. I mean, which form you started with. So there is one form which talks about these rays. You trace the rays. So that is, you end up an equation which is di nu ds, where s is the path length, equal to something like this. That is basically the character, what we call characteristics of these equations. So partial differential equations have characteristic solutions. So basically, so this is a I nu is a function of t and x and n. So you can solve at every point in space in every direction and everything. But what you can do is you can trace the light rays, basically, or the photon rays. So that will give to that equation. So that equation is basically derived from this. This is more fundamental. Okay. I mean, this is something which you can derive from what we call Boltzmann equation or phase space distribution functions and things like that. Okay.
thank you.
Or Maxwell's equation. So this is the fundamental equation.
Yeah. So in the plot where you showed how the the plot that you showed in the morning as well, that how the matter power spectrum will change if you have warm dark matter.
Yes.
So
yes.
there the 2 kV, 3 kV, what is that? I mean, I don't get it. Is it the mass of the dark matter particle?
Yes, mass of the dark matter particle, assuming it to be assuming it to be a thermal relic. Yes. So sterile neutrinos, for example.
I see.
Yes. Yeah. So
Okay.
this is the mass. So 1 kV will have more suppression, 2 kV will be less, and so on. Okay. By the time you hit 7 or 8 kV, and it's almost indistinguishable from CDM at the scales which we are probing with Lamin alpha forest.
But I mean, so is it assuming that all the dark matter is in the form of this warm
There's
component?
just one dark matter. Yes, that is an assumption. So there are many other models which can give suppression. For example, there could be non-thermal relics as well. It is axionic. That also can give suppression in these scales, but the corresponding masses will be completely different. It's 10 to the minus 21, 10 to the minus 22 electron volt.
And in this plot, I mean, are we not taking care of normalization? Because
so the normalization is done using CMB basically. So we know what so CMB will probe somewhere around these scales, and we know what is the power spectrum at those scales, like AS or something.
no, what I'm asking is, so let's say we have this red or green scenario instead of the blue one. So does it affect the value of omega m also, the omega matter?
Okay, so in principle, so this is assuming everything else to be constant, and I'm plotting the predictions. Okay, now what you will get by comparing with data is a different matter. So there, that is what I'm constantly saying, that you should be able to vary all the cosmological parameters along with the warm dark, I mean the whatever dark matter model you have. Because if you don't do that, you will be missing something. It turns out that most of the cosmological parameters, that the way they have put in, the constants on omega m does not change much.
Okay. And second question is, so for for observing Lyman alpha transition, why do we need quasars? For example,
Because you need a background. Right?
no. For example, CMB is redshifted to low to high wavelengths now.
Huh? CMB is restricted to high wavelength.
The microwave
lower
region now.
frequencies.
Yeah.
There is virtually no CMB photons in UV. Otherwise, you will see CMB in the optic.
No. What I'm saying is that at high redshift, CMB was of higher energy, right?
But at high redshift, anyway, Lyman alpha, I mean, even then, Lyman alpha forest is a completely different frequency. CMB at those frequencies would have been at redshifts above CMB actually. See, Lyman alpha, the difference between the two energy levels correspond to somewhere around 10 to the 4 Kelvin. So when was CMB of the order of 10 to the 4 Kelvin? It was before the CMB was.
No, but there's a high energy tail also, right?
That doesn't make any difference to this kind of, I mean, it's exponentially falling. So by the time we are observing Lyman alpha, CMB is at redshift 6. CMB is what? 6 times 3, 20 Kelvin. We are talking about 10 to the 4 Kelvin. No high energy tail will give you that. So you have to have galaxies or quasars, something.
Why don't galaxies work?
Galaxies are just faint, just too faint to see the that Lyman alpha forest. It will be like consistent with 0.
Okay. And somewhere during the talk, I'm not sure whether you said this, but I think you said that the small halos are more likely to form stars. Did you say this?
From the first. The first stars are more likely to form in smaller, relatively small.
Yeah. Can you tell me briefly why is that the case?
Because small mass halos form first. So if the first stars want to form, that will be the natural place where they will form. Of course, you cannot form stars in too small halos because they won't be able to cool. 10 to the 8 solar mass halos are the typical ones which can cool, and that's probably where the first stars will form. Not in 10 to the 10 solar mass halos, because they will form much later. By the time there will be enough 10 to the 8 solar mass halos which will allow us to form stars.
Thank you.
You had? Yes. Which one? The one to do cosmological parameters or to do fluctuations?
No, the cosmological parameters.
Yes.
Does it take into account nature of dark matter And also another thing, so this global standard 21 centimeter signal is it the background? Or- Because we,
Yeah. So in our code, it can account for, I mean, the convention, the default version does not take that it just assumes cold dark matter. What we now have is a version where we can put in at least the thermal relics, because we know how the power spectrum changes. But what we plan to do is we plan to next go to a kind of model. Let me go back, where we really don't commit ourselves to any particular dark matter model, but just model the suppression using some fitting
this
function.
would be the,
Yes. So what we will then constrain is, yes, the suppression scale, how fast it is falling down, these
so
parameters.
if we have any dark matter which could follow this kind of.
Yes, yeah, and we will have enough kind of freedom in the parameters so that this shape can be varied in different ways, and people have done that. It is not like we will do it for the first time. So there is this ethos kind of, there is something called ethos, that is another one
Second
paradigm.
thing, does it take into, I mean, does it take the standard 21 centimeter signal that we expect from the standard cosmology? Because
So the model actually calculates the 21 centimeter signal, and you have to give it a data to fit. Now, if you give it edges data, it will find it very difficult to fit. You have to do many things to get it fit. So, but if hopefully if there is a more standard data, which we don't have, it will fit much more
we don't
nicely.
have any simulation from the this average standard signal that we expect from theory. We don't.
But this model is the theory in our case.
Yeah, that's
What we then, I mean, since edges is now gone and we don't have any observations, we create mock data, assuming something, and then we try to see what kind of forecasts we can make on the various parameters.
So do we have that different forecast that we can?
So for the thermal relic we have. So what I tried to show, I think in the morning, what I tried to say is that suppose the thermal relic is actually CDM, like a GeV kind of mass particle. Then with the 21 centimeter data, along with all the other data, you will be able to constrain it, and you will be able to say that it is larger than 7 point something keV at that level. However, if it turns out that the thermal relic has, let us say, a mass of 7 keV, we will be able to detect it. We will be able to say that it is between 5 and 10 keV, for example. So there will be a detection. In the other case, we are just ruling out. There is no detection per se. If it is 7 keV, we will be able to detect it. If it is lighter than that, we won't be able to detect. If it is lighter than that, it will be easier to detect, sorry, and so on.
Maybe the last two questions, perhaps.
So I have a question is that during the dark ages,
Yes.
there will be 21 centimeter lines, right?
There are, yeah, neutral hydrogen hence 21 centimeter lines. Yeah, this is the dark edges part.
Yeah. So does that will give us a probe for structure formation?
That will give us a probe for the underlying dark matter power spectrum, because dark edges, no galaxies have formed. So neutral hydrogen is tracing the dark matter for all practical purposes. So if we can detect this part, we will be doing really cosmology at very, very accurate. The problem is these are really low frequencies, 20 megahertz and things like that. Now that cannot be done with, because of the ionosphere, you cannot do from the ground. You have to send something to space. The other problem is there is just too much interference. I mean, the signal here is very weak, and it's just too much signal from radio signal from the Earth. I mean, our mobiles, our satellites, our other things. So currently the plan is to send a satellite to the other side of the moon, so that all the interference from the Earth gets hidden. So the Chinese and the Dutch sent something that did not work. Okay, so but they did the first. But there are a lot of efforts being kind of planned, including one in India, one led by RRI. They are along with ISRO. There is a plan to send a satellite which will go around the moon, and when it is on the other side, it will give us signal. But then there are other groups in the US and all who are also planning to do that. So we'll have to see.
So
And yeah,
this is for the global one, right?
this is the global one.
But I was thinking that in the global one, I mean, how there is a deep system.
This dip, because the gas is colder than CMB. Because the gas temperature falls as 1 plus z square or 1 by a square, and the CMB temperature falls as 1 by a. The gas temperature falls much faster. Gas temperature falls faster because the temperature is essentially proportional to P square for non-relativistic particles, and P goes as 1 by a. So T goes as 1 by a square. Whereas in the case of ultra-relativistic particles, T is proportional to P, basically momentum. So that is why. So the gas is cooler than CMB. As a result, it will absorb more CMB photons than emit. So you will see this. It's probably the last one. Yes.
I have a question about this statement that neutral hydrogen is an unbiased tracer of the dark matter density.
Unbiased tracer under certain conditions. Yes.
So yes, so is this only valid before reionization starts?
Yes.
Yes.
I mean, yeah, it is actually even okay. Yeah, neutral hydrogen density before reionization is a reasonable tracer of the underlying dark matter, particularly at large scales. At small scales, there are differences, but if we are talking about things like global signal or power spectrum at large scales, it's a very good approximation. At small scales, there are baryonic effects, pressure and other things start to play a role.
Okay. And after reionization starts, as you showed, the power spectrum of neutral hydrogen varies in a very complicated way.
Yes.
With time.
Yes.
So in that case, is it like easy to model the bias and then use it to trace the dark matter?
Okay. So that's a good question. So what happens is at very large scales, at scales which are larger than the typical sizes of the bubbles, at those scales, the neutral hydrogen power spectrum, the slope is basically following the dark matter with a different amplitude. So it's just a biased tracer of the underlying dark matter power spectrum. Okay. So in principle, at large scales, if you can detect the power spectrum, it's slightly larger than this. You have to go to 10 to the minus 2 or something in this range. Okay. Then in principle, one can understand, at least get the slope of the dark matter power spectrum at those scales. There are problems in trying to detect this at very large scales. Okay. That's a different matter altogether.
Thanks a lot, Tirth, for the extremely comprehensive and very
thanks.
well delivered.
Thanks the others for staying here.